So, good morning, everyone. And today is
Morning, sir.
lecture number 18. And I think in the previous class, the power went out. What we are discussing in the previous class, do you remember? What was the
Sir,
topic of discussion? Yes? What we are discussing in the last class?
emissivity.
No, not emissivity. Emissivity was already done. We have done emissivity. We have done Kirchhoff's law. What was the point of discussion in the last class? Please go through your notes. Are you making notes, hopefully? Tell me what was there. What
Distribution
was
of
there in the
energy.
last class? Yes? Tell me.
Distribution of energy in the spectrum of blob body.
We were discussing the spectral distribution of thermal radiation. Yes or no? Do we remember it? Spectral distribution of thermal radiation. We had drawn a graph. Have you drawn that graph? This graph. Have you drawn it? I asked you to draw it. Did you draw it? It's a very important graph that has come once in JEE. When I say JEE, I mean JEE Advanced. And we are expecting, I hope, expecting that you can get this question anytime. Have you drawn this graph? Have you drawn this graph, beta? If no, then please draw it. Draw this graph. It's an important graph. As I told you, questions in thermal radiations look very confusing, but they are actually very simple. They are based upon concepts, and if you know those concepts, you should be able to solve any question, whether it's with graph or it's not with graphs. And as I told you, radiation is one topic which is not covered nicely in any of the classes that I have been to. So this normally remains weak for all the students. You don't give enough attention to radiation. We are going to solve it carefully so that if a question comes, you should be able to solve it and get ahead of other students. Have you drawn this graph now?
Okay, sir.
As you can see, there are three temperatures, T1, T2, and T3. T1 is the smallest temperature, T3 is the largest temperature, and T2 is in between. Now, based on the graph that you see, there are some important points that you must remember and note down. What are the important points that you must remember and note down? What is point number one? What do you think? Look at the graph and tell me what all things you see. This is a graph between E lambda and lambda for thermal radiation emitted by a body. What all conclusions we can draw from this graph? This will make you understand how to read a graph. That will come in your, that is a part of your maths. Basically, graphs are not in physics, taken from maths, but they have much relevance here. What you can understand from this graph, point by point, if you understand and note it down, every question that comes will be from those points, 5 or 6 or 7 points, whatever. What is the first thing that you must understand? Tell me.
Explain, sir.
Yes, beta.
Explain karo.
Explain to मैं करूंगा ही. But what do you understand? Do you understand anything looking at the graph? I'll explain it. Do you understand anything that you look at the graph? Can you draw any inference from the graph? मैं तो explain करूंगा ही. I'll explain. That's my job. But what do you understand from the graph? It's a simple graph. X axis, Y axis. Do you understand anything?
As lambda increases, E lambda decreases.
As lambda increases, E lambda increases. Is that so, or it changes? It first increases, then decreases. Yes or no?
Yes, sir.
So what is the first point that you write? The first point that you write is, if lambda increases, E lambda increases. Or instead of writing it in this way, see, remember there are three things in this graph. One is E lambda, one is lambda, and the other one is temperature. So everything should be having all these three quantities that you understand from this graph. So instead of writing it like this, if lambda increases, E lambda increases, that is not the correct way of understanding it. What we can say, for a given temperature, see there are three temperatures given here, T1, T2, and T3. For a given temperature, if you take any temperature, you take temperature T1 or T2 or T3. For a given temperature, the distribution of energy with lambda is not uniform. For a given temperature, I hope you are noting it down. For a given temperature, the distribution of energy, distribution of E with lambda is not uniform. Do we understand?
Yes, sir.
That means what? If I have a body, this is the body, its temperature is more than 0 Kelvin. If it is more than 0 Kelvin, it is going to emit thermal radiation. But it is not going to emit thermal radiation of one wavelength. It is going to emit thermal radiation of all the possible wavelengths that are possible from 0 to infinity. But what you have to understand is, it is not going to emit equal energies of all wavelengths. That means for some wavelength, the energy emitted would be less. For some wavelength, the energy emitted would be more. For one particular wavelength, this energy is going to be maximum. Do you see this here?
Yes, sir.
So that is one of the most important things that you must understand from this graph. For a given temperature, distribution of how much energy of how much wavelength I am emitting, any body is emitting, that is not uniform. If that is not uniform, then what happens? Then for a given temperature, you must remember that, because temperature is one of the quantities. For a given temperature with wavelength, energy first increases, reaches a maximum, and then decreases. Do we understand this?
Yes, sir.
You can see here with temperature T3, first energy with wavelength is increasing. It reaches a maximum and then it decreases. Is everyone following me? Yes or no?
Yes, sir.
Okay, that was point number 2. Then what is point number 3? Since we have talked about the maximum, for a particular wavelength, this energy emitted is maximum. Do you see this? For a particular wavelength, energy emitted E lambda is maximum. Do we see this? Yes or no?
Yes, sir.
That is the most important thing, because this is known as your Wien's displacement law. Now, how do we understand this Wien's displacement law? Have you heard about Wien's displacement law?
No, sir.
You have not heard about Wien's displacement law? What is this Wien's displacement law? I guess you have not read radiation, but it's okay. As I told you, not many students They give attention to radiation because sometimes this topic just goes above our head and we don't understand it correctly, and that is why we need to spend some time on it. Wien displacement law, I have made the diagram larger. Now, what is this Wien's displacement law? Up till now, what we have seen is when I increase temperature from T1 to T2 to T3, up till now, I was concentrated with only one temperature. At any given temperature, for example, T3, we have lambda 3, where the energy emitted is maximum. For the temperature T2, we also have lambda 2, where temperature is maximum. For a given temperature T1, we have a lambda where the energy is maximum. Do we understand this?
Yes, sir.
But you see a big similarity between, a big relation between T1, T2, T3 and lambda 1, lambda 2, lambda 3. I made the diagram bigger. Can you tell me T3 is the largest temperature, T1 is the smallest temperature, T2 lies in between. Look at lambda 1, look at lambda 2, look at lambda 3. Corresponding to T3, we have lambda 3. Corresponding to T2, we have lambda 2. And corresponding to T1, we have lambda 1. If you understand this, you have understood Wien's displacement law. What do you see? T1, T2, T3. What do you see? Lambda 1, lambda 2, lambda 3. T3 is more than T2 is more than T1. What do you can say about lambda 3, lambda 2, and lambda 1?
As temperature decreases, lambda value increases.
As temperature decreases, lambda increases. Or I say ulta. When temperature increases, lambda decreases. Yes or no?
Yes, sir.
That is the next point. That is Wien's displacement law. So if I write it here, bacha, T3 is more than T2 is more than T1, then I write lambda 3 is less than lambda 2 is less than lambda 1. Do we understand this? Are we all noting this down?
Yes, sir.
That means point number 4 is as temperature increases, lambda maximum. You understand lambda maximum?
Yes, sir.
As temperature increases, lambda maximum decreases. The maximum energy wali wavelength decreases. And it decreases in such a way, that the product of lambda n and capital T, product of lambda m and capital T, remember capital T is in Kelvin, lambda is in meters. The product of lambda m and T is a constant, and this law is known as which law?
Wien's law.
This is known as Wien's displacement law. Lambda m into T is a constant, and this law is known as Wien's displacement law. Do we understand this?
Yes, sir.
Pakka? We have understood 4 points up till now. Any doubts on these 4 points? I hope you have noted it down. All the 4 points. Yes or no?
Yes, sir.
Pakka?
Pakka, sir.
Pakka? कच्चा वाला पक्का या पक्का वाला पप्पा? कच्चा वाला पक्का या पक्का वाला पक्का? I mean the good wala, I mean confidence wala pakka, that we have understood this?
Yes, sir.
Okay. Coming on to Wien's displacement law, we have written point number 1, 2, and 3. Point number 4 is Wien's displacement law. We also need to know the value of this constant. That is what I'm going to write. So point number 4 is what we have written, lambda m into T is a constant, and this constant is sometimes written as B. And there are many questions that have come on this simple concept in JEE Advanced. Lambda m into capital T is a constant which is equal to B. The value of this B you may not know, but this is just for your information. This value of B is 2.88 into 10 to the power minus 3 meter Kelvin for a black body. Most of the question that you will see will be based on black bodies, will be based on this concept, a simple concept of Wien's displacement law. When you increase temperature, the maximum wavelength, the wavelength at which maximum energy is emitted, it decreases. Do we understand this? Again, I'm asking you.
Yes, sir.
Now, what is a practical example of this? Do you see this in daily life? Can you prove it by something that you have seen in daily life? Have you seen this happening in daily life? We have discussed. We have discussed point number 1. We have discussed point number 2. We have discussed point number 3 as given in your notes. In point number 3, after point number 3, I have added point number 4. I have put Wien displacement law in point number 4 in your book, in your notes, in your sheet. It is given in point number 3 only. Question is, do you see this Wien displacement law happening in your daily life? Have you ever seen a gas burner? When you start a gas burner, put the lighter on. Can you tell me what is the color of the flame of a gas burner? What is the color of flame of a gas burner? Do you know this? Yes or no? You have never boiled water or boiled milk on your gas, the gas that you have at your home, gas stove. Have you never boiled anything? Never made an omelette? Never made a Maggie? Never make a cup of tea? You remember the color of the flame?
Blue.
Blue. Now, if you remember, the color of the flame is blue, and I hope you remember this. Vibgyor, do you remember this Vibgyor?
Yes, sir.
In which order is this Vibgyor arranged? In the increasing order of wavelength, yes or no?
Yes, sir.
Pakka na?
Yes, sir.
Kacha wala pakka, pakka wala pakka. This is how wavelength increases, yes or no?
Yes, sir.
Now, you see this flame for gas burner, and if you just sprinkle some drops of water on that gas flame, does it change color?
Yes,
Does
sir.
it change color? Yes or no?
Yes, sir.
It changes color. Why does it change color? Because when you put some water, the temperature goes down. Yes or no?
Yes, sir.
What color do you see when you sprinkle some drops of water on it? What color do you see?
Red color.
Red. Now, do you understand why it becomes red? Now, do you understand why it becomes red?
Yes, sir.
Why? Because the temperature of that flame goes down. And when the temperature of that flame goes down, the maximum energy that it is emitting, the wavelength comes up, the wavelength goes up. And therefore, instead of a blue flame, you start to see a red flame. So if I now ask you, which flame will have a higher temperature? Violet, indigo, blue, green, yellow, orange, red. So which will have
Violet.
the highest temperature? Violet is the highest temperature. You see something violet, red, we call it red hot. You have a piece of iron or you have a piece of copper, you start heating it up. It gets black, 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 black. And after some time, it becomes red hot. Have you seen it? Red hot. Why it starts to become red? When you are heating it up, it is emitting thermal radiation. It is emitting thermal radiation at all temperatures. You are heating it up, it is also emitting thermal radiation. But it is emitting thermal radiations more than infrared. If it is more than infrared, you don't see anything. But when the temperature increases, lambda decreases. Yes or no?
Yes, sir.
When this lambda comes in the range of visible light, you start seeing it red. Red hot. What is more hot than red hot? Orange hot is more hot than red hot. So in summer times, when you look at the sun, it is more likely orange, but when it is setting, it is more likely red. Do you understand the difference now?
Yes, sir.
The red sun is probably emitting less. The temperature is probably less. The temperature that you feel. You understand this? Right now
Yes.
it is violet. Right now it is orange or violet. Violet means it is very hot. So if you increase the temperature, first it will become red, then orange, then yellow, then blue, then green, then blue, then indigo, then violet, and after that you will stop seeing the color. Do we understand this?
Yes, sir.
Paka? This law is known as,
Wien's displacement law.
when you get into an engineering college, which I'm sure you will be doing gas cutting. You will be doing a lot of welding exercises. When you are cutting metal or anything with gas, we call it acetylene gas cutting. You will be adjusting the color of the flame by adjusting the oxygen and whatever all things gases. And then by looking at the color of the flame, you will be able to make out whether this flame is hot or not, whether it will be able to cut. If you have to cut, the flame has to be blue. Otherwise, you will not be able to cut. When you don't have to cut, you have to weld. The flame has to be of a different color. Do we understand this?
Yes, sir.
And that is how these welders, they adjust the drilling, and then they look at the color and then know that now I can weld. Now it is not hot. How did they see it? They see it by the color. They may not know Wien displacement law, but they know what is the application for this Wien displacement law. Am I clear?
Yes, sir.
That was point number how much? 4. That was point number 4. The next point is point number 5. Point number 5. And what is this point number 5? In order to understand this point number 5, you again have to go back and look at the diagram. You again have to go back and look at the diagram. For all wavelengths, an increase in temperature causes an increase in intensity. Do we understand this? What do I mean by this? When I increase temperature, what happens? We have seen the 4 points. We are not going to discuss those 4 points because they are already done. What we are going to discuss is the next point, which I have written it as the 5th point. Now, look at one particular wavelength. If I look at this wavelength here, this wavelength lambda here, at temperature T3, the energy emitted at lambda is this much. At temperature T2, the energy emitted is this much. And at temperature T1, the energy emitted is this one. Do we understand this?
Yes, sir.
What relation between I see at a particular lambda when I increase temperature? So, again, try to understand it in terms of simple language. This is the body. It is emitting thermal radiation. It is emitting thermal radiations of all different wavelengths. For one particular wavelength, this energy is maximum. We have understood this. If I increase the temperature, that particular wavelength will decrease. I have understood that. What I'm going to understand right now is, for example, a wavelength of 1 meter, it is emitting some radiations. When I increase the temperature, same wavelength, but the energy emitted will be more. Do we understand this?
Yes, sir.
If I increase the temperature at any given wavelength, the energy will also increase. Have you noted this point?
Yes, sir.
For a given wavelength, when I increase temperature, the energy emitted also increases. With an increase in temperature for a given wavelength, the energy also increases. That means energy is proportional to the temperature increase. And we will see how much is that proportion in the next topic, which is Stephen's law. Have you heard about Stephen's law? Yes or no? Now, these two are the most important points that have come. I think one of these points has come in a JEE. The next point has not come, and probably I can expect that this point can easily come, and most of the students would be confused with these points. So here comes point number 6 and point number 7. Can anyone read point number 6 for me?
The area under the curve integration of E lambda into D lambda will represent the total intensity of radiation at a particular temperature. This area increases with rise in temperature of the body.
Bus. Do we understand this? When I
Yes.
increase the temperature, the total area under the graph increases. That means the total energy which is emitted by the body is going to increase. Yes or no?
Yes, sir.
I increase the temperature of this body. for a particular wavelength, energy increases. The overall energy also increases, yes or no?
Yes, sir.
That means this energy emitted is somehow proportional to temperature, yes or no?
Yes, sir.
And what we have found out that this energy is proportional to what? Next line, read it.
It is found to be directly proportional to the fourth power of absolute temperature of the body.
It is proportional to the fourth power of the absolute temperature of the body. Total energy is proportional to T raised to the power 4. And this, gentlemen, this law is known as the Stephen's law. Do we understand this?
Yes, sir.
Paka? We are going to study Stephen's law in detail. Right now, we just need to understand that it is proportional to T raised to the power 4. Have you understood this problem number 6? Can I have some raised hands? Have you understand this? Okay. Then comes point number 7, and which is the most important point, and I don't know why, but I feel that this can come directly in your book, and most of the students will write the answer as T raised to the power 4, but the answer is not T raised to the power 4, answer is T raised to the power 5. Can you now read the question? Can you now read the point?
The energy E maximum emitted corresponding to the wavelength of the maximum emission, lambda m, increases with the fifth power of the absolute temperature of the black body.
Remember, the maximum energy which it emits is proportional to T raised to the power 5 and not T raised to the power 4. And this is one point which everyone in the examination hall, almost everyone in the examination hall will write as T raised to the power 4. Remember the difference between 6 and 7. Do we understand the difference between 6 and 7?
Yes, sir.
In 6, I am talking about the total energy. Total energy is proportional to T raised to the power 4. In point number 7, I am talking about the maximum energy that is emitted. That maximum energy that is emitted is proportional to T raised to the power of 5. Will you remember this?
Yes, sir.
That is all about Stephen's law. No, it's all about the thermal radiation distribution, and there can be a question in JEE Mains as well as JEE Advanced based on this. And to make my point more clear, as I told you, there was a question that came and no one at that point in time was able to answer this. This is the one that comes to you. Tan, tan. JEE 2000. Now, you must understand that questions can be wrong in JEE as well. Here also something is not correct. And what is that thing that is not correct? This T2, gentlemen, should be a bit higher. Okay, it should be like this. Now, this should be T2. What is the answer? What is the correct sequence? Which temperature is more, which temperature is less?
T1 greater than T3 greater than T2.
T1 greater than T3 greater than T2. So you can understand, if you know the graph, you should be able to solve simple questions. And this was a question when everyone bamboozled because they had no idea about this question. Do we understand this? Yes,
Yes.
or no?
Yes, sir.
Well done. Then this is a question, and I hope that similar question can come anytime in a JEE. When I say JEE, I mean JEE Advanced, and here is the question coming up to you right away. The adjoining diagram, again, if you have no idea about the diagram, you will never be able to solve this question. The adjoining diagram shows the spectral energy distribution E lambda of a black body at two different temperatures. The area under the curves are in the ratio 6:1. What is the value of temperature T? The question passes on to you. Will you be able to solve this?
Yes, sir.
Then I will give you time to solve it. You have 4 answers as well. 32,000 Kelvin, 16,000 Kelvin, 8,000 Kelvin, 4,000 Kelvin.
4,000 Kelvin.
4,000 Kelvin is what you get, and let me see whether the answer is correct or not. Yes, my dear friends, the answer is correct. All of you got the answer?
Yes, sir.
Well done. This was not possible if you had not known about the graph and what the area under that graph gives you. And the area under the graph gives you the energy, yes or no? Total energy, yes or no?
Yes, sir.
And this total energy is proportional to absolute temperature ratio to the power 4. We have not done Stephen's law, but we have seen this in this particular topic. So we can go ahead and solve this question. After that, it is pretty damn simple. ET divided by E1000 is capital T divided by 2000 raised to the power 4. And from there, you can get the value of the temperature as 4000 Kelvin. Can we move ahead with the next question? Yes or no?
Yes, sir.
As you can see, the questions are simply based on what we see in the graph and what we understand from the graph. If you understand this, you will be able to solve this. Else, bye bye, 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 bye bye. And here comes a question. Now, this question has got 4 graphs. I can only get 2 graphs on your sheet, on your screen. So let us have a look at the 2 graphs and then give the following graph shows the correct variation in intensity of heat radiation by a black body and frequency at a given temperature. 2 graphs are here, and you have to find out which is the correct graph. Graph number A. Now remember, this is how questions are framed in an examination hall. It tests your understanding of the topic different ways. Graph number A, something. Graph number B, something. Have a look. Have you seen graph number A and graph number B?
Yes, sir.
But I can't get all the other. So I'll now get graph number C and graph number D and then hope for the results. Hope for the results. Hope for the results. And here comes my dear graph number B. Remember, down below is frequency, is not wavelength. Frequency and not wavelength. Frequency and not wavelength. Frequency and not wavelength. That is graph number C and D. Frequency.
C.
And the answer is?
C.
Why is the answer C? Because when lambda decreases, frequency should increase. Do we understand this?
Yes, sir.
That is the correct answer, my dear friends. The answer is definitely C. You can see that if you understand the problem, you have the solution right away. Do we understand this? Yes or no? Can I move further ahead with some more questions?
Yes, sir.
Yes, sir. No, sir. Better I go, sir. Better we go, sir. And again, as you can see, this is a favorite topic of JEE, and the JEE that I am talking about is not now wala JEE. It is the JEE of my time, and JEE of my time was considered to be more difficult than the JEE of this time. And I told you, radiation, whenever they give you a question, the question looks very difficult, but it is pretty damn simple. The black body is at a temperature of 2880 kelvins. Energy of radiation emitted by this object is wavelength between 499 nanometer and 500 nanometer is U1. Oops. Between 999 and 1000 is U2, and between 1499 and 1500 is U3. The main constant is Falana. What is Dhimaka? U1, U2, U3, U4. Oh, I mean A, B, C, D, IIT-JEE 1998. Dun, 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 dun. Dun, 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 dun. Dun, 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 dun. Dun, 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 dun. Any idea?
Yes, sir.
Yes, sir. No, sir. Better I go, sir. Better you go, sir. Actually, if I had to modify this question, I will ask you to do this question in this way particularly. You must understand what is the relation between U1, U2, and U3. 1, U2, U3. Which will be higher, which will be highest, which will be lowest. That is how I shall put the question in today's scenario. The pattern passes on to you. U1, U2, and the U3. Give you a minute to think about it. Think. It's IIT-JEE 1998. Yes, my dear friends, any answer?
U2 is highest.
Which is highest?
U2.
U2 is highest. How did you get it?
By calculating the lambda value.
By calculating the lambda maximum wala value, you will understand that U2 is highest. Yes or no?
Yes, sir.
You all understand this, correct? Now, once you understand this, you should be able to make out the rest of the question. That is why the value of B was given. The value of B was given so that from Wien's displacement law, you could calculate the maximum intensity wala lambda. Yes or no? And there was a reason it was given as 2800 and something, so that temperature was given, so that you can calculate the value of lambda maximum as 1000 nanometer. Yes or no? Yes or no?
Yes, sir.
That's it. And once you understand this, you will be able to understand that at 1000 Kelvin, the energy would be maximum. Then U2 will be maximum, U1 will be smaller than U2, and U3 will also be smaller than U2. It would be difficult for us to understand the relation between U1 and U3 because the graph is not symmetric, and it becomes a complicated question to relate U1 and U3. You may not be able to relate U1 and U3. You can still relate U1 and U3. I told you it is proportional to T raised to the power 5. Yes or no?
Yes, sir.
So if temperature is high, U3 should be higher. Getting my point?
Yes, sir.
But still, you can understand that U2 will be maximum. Do you understand this? Can I have some raise hand that you understand this? Are you in the class? Do you understand this, Becha? चलो 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 कहाँ चले? Where shall we go? And now we will try and understand the last, not the last, the second last topic of this chapter, and the name of this second last topic of this chapter is known as this. What is the topic known as? Topic is known as Stevens Law. Stevens Law. Stevens Law. Anyone has heard about Stevens Law? Some people also call this Stephen Boltzmann law because this constant that comes is known as the Stephens or the Stephen Boltzmann constant. This law was given by Stephen and then it was proved by Boltzmann. Therefore, Stephen Boltzmann law, Stephen Boltzmann constant. Have you heard about Stevens law? Yes, sir. No, sir. Yes, sir. No, sir. Heard about Stevens law? Say something, sir. Don't keep quiet, sir. Have you heard about Stevens law? Either you have heard it, it's a binary question, 0 or 1. Heard it? Binary 1. Not heard it? Binary 0. 0 or 1?
0.
0. But 0 can become a hero, 1 cannot become a hero. So now we're going to become heroes. Stevens law. If I go back 5 minutes in the past, I can somehow go back 5 minutes in the past. It's not possible in real life, but in physics it's possible. If I go back sometimes 5 minutes earlier in this class, if I go 5 minutes earlier in this class, where will I go? Tell me, where will I go? Ting, 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 ting. Ting, 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 ting. If I go 5 minutes earlier in this class, I'll arrive at this junction. Do we remember this junction?
Yes, sir.
Point number 6. Do we remember point number 6? What was point number 6 telling us?
Total energy is directly proportional.
Total energy is directly proportional to 10 to the power 4. And I have also marked Stevens law. Did you pay any thought on that Stevens law at that point in time in the past? 0 or 1? 0 means no. 1 means yes. Yes.
Yes,
0.
sir.
0 again.
1.
1. Okay. 1. So you are number 1. So you know you cannot get a higher rank than 1. 1 is the topmost rank that is possible. Stevens law, and that is what Stevens law states. Now remember the statement and remember it in the way that it is written here. So this is the best possible way you can write in statement. Otherwise, it just gets confusing. And that is why symbols are very important. Do you remember the symbol E, capital E?
Total energy.
No. Oh, that is the problem, that you don't remember the symbols and you make your own variations of the symbol. What was capital E standing for, bacha?
Emissive power.
Total emissive power. Please don't forget it. And what was total emissive power? Again, go back in the past, in the previous class. Now you'll have to check your notes probably. Check it from the note. What was total emissive power? As I told you, this chapter is all about understanding the definition. And if you mix up the definition, you are gone, my dear friends, without even fighting for. Go back, go back, go back, go back, go back, go back, go back. In the past, in the past, in the past, and find out what was total emissive power.
Total amount of thermal energy emitted per unit time.
You forgot per unit area?
Area of the ball.
It was per unit area also, no? Yes or no?
Yes, sir.
Who will say area? The total radiations emitted per unit area per unit time. Did I say that? Yes or no?
Yes, sir.
Did you write that? Yes or no?
Yes, sir.
0 or 1? Binary answer. Remember that? 0. If you don't remember it, 0. Remember it, 1. 0 or 1?
1.
1. So emissive power is the thermal radiation or radiant energy or radiations emitted per unit area per unit time. Will you remember it now?
Yes, sir.
Because the same term is coming in. We were using the same term everywhere. Even in Wien displacement law, we use E lambda, spectral emissive power. The area under that graph gives us total emissive power, energy emitted per unit area per unit time. Do we understand this?
Yes, sir.
According to this law, the radiant energy emitted by a perfectly black body, remember Stevens' law is for a perfectly black body, per unit area per unit time, which is your emissive power, do we understand this?
Yes, sir.
Of a black body is directly proportional to the fourth power of its absolute temperature. So emissive power of any black body is proportional to T raised to the power 4. If I remove the proportionality sign, one thing will come for the body and one thing will come as constant, and that constant is known as sigma. Not sigma. This is known as the Stephen constant or the Stephen Boltzmann constant. The dimension is panana, and the value is dhimaka. Do we understand this?
Yes, sir.
Please I note down the dimension because this question can come in dimension. It is very easy to get the dimension. The value you may not know this because if this is required, it will be given in the question. Do we understand this?
Yes, sir.
Now this what? This law is only applicable for a black body, Kali body, but all the bodies are not Kali bodies. So if you have a body which is not a black body, what will be the Stevens law for a black body or any body in general? To write the Stevens law for any body in general, what do? You multiply this entire term by E. Do we remember E? Small e.
Emissivity.
What is small e?
Emissivity of the body.
And how do I get the emissivity of the body? What is the relation between emissivity and how did I define emissivity? Again, go back in the past. See, if you have to go back and look at your sheet bar, that means you have not studied what you have done in the previous class, and this class goes to waste. Yes, what was emissivity?
Ratio of total emissive power of the body to the emissive power of a perfectly black body.
Now, if you have to look back in the past, my last class has gone down the flush. It has been flushed out of your system. That is a bad sign. You only flush the waste particles in your body and your system out of your body. You don't flush your lungs and kidneys out of your body. Do you flush them out? One day if you know my lungs are not doing good, let me flush it out. Will you be able to flush your lungs out of your body? Yes or no? Tell me. Or you feel like let me flush my eyes out of my body, so I'll flush it. Oh, up, it's gone out. Can you do that? 0 or 1? 0 is no. 1 is yes. Tell me. We only flush out the non-essential commodities. That is why we call it flush. Cleansing of the system. You don't flush your essential components out of your body. When the component becomes bad, then only you flush it out. My kidneys are not working, I would probably probably flush one out. Unless and until it's not bad, I will keep it. Don't flush it out. E is the emissivity of the body. Emissivity again is the ratio of emissive power of any body divided by emissive power of Kali body, black body. From here, I can find the emissive power of any body. Emissive power of any body will be emissive power of black body multiplied by. So now, if I write this Stephen's law in terms of E, this becomes applicable to all the bodies in the universe, whether they are black bodies or white bodies or green bodies or brown bodies. Do we understand this?
Yes, sir.
Pakka? Kacha wala pakka, pakka wala pakka. Kacha wala pakka is 0, pakka wala pakka karo. Kacha wala pakka is 0, And pakka wala pakka is 1. 0 or 1?
1.
1. Okay. That was emissive power. Now remember the relation between emissive power. Then I'll write it because it would be flushed out of your system. Emissive power is total energy emitted per unit area per unit time. Do we remember this?
Yes, sir.
From here, I can calculate or find out the total energy emitted. If the delta Q is the total energy emitted, that will be equal to AT small t E small e sigma T raised to the power 4. Remember, T must be in Kelvin. Yes or no?
Yes, sir.
This law is known as which law? Stephen's law. For a perfectly black body, what is the value of E small e small e? What is the value of small e for a perfectly kali body?
1.
What is the value of E for a perfectly black body? E for a black body. How much is E for a black body? Again, you have to go it back in the past. Everything has been flushed out of your system. Not good. Your cleansing system is too good. You're cleansing out everything from your body. When you're going to give JEE, I hope that you retain something. Will you? Yes or no?
Yes, sir.
Okay. What was the emissivity of a black body? Tell me the answer.
1.
1. What is the emissivity of a perfectly reflecting body?
0.
Remember. What will be the emissivity of any body which is not a perfectly reflecting body and which is not a black body? It will lie between any other body in the universe. Emissivity will lie between
0 to 1.
0 to 1. That is how we finish the course. 0 to 1 finally. 0 means no, 1 means yes, 0 means off, 1 means on. We are right now on, and when you come for the next class, what will you do before coming to the next class?
Should read all the previous notes.
Should read all the previous notes. Do not flush these notes out of your system, because if you do it, the entire class for today goes in vain. Not Wien's displacement law, but VAIN vain. That means it goes down the flush. Don't flush it out. You only flush the waste particles out of our body. This is not waste. So on that note, I will wind up this class. We have had a view about Stephen's law. I'll do one or two problems on Stephen's law, because again the problem on Stephen's law comes and everybody is bamboozled because they don't know how to do it. And again, the questions are more likely to come in JEE Advanced rather than JEE Mains. So we'll wind off this class here. And I'll see you first thing in the morning on Monday. Remember to read your note before coming to class. Do not go back in the past. Take care. Have a nice day. If you have any doubts, please ask me. Bye-bye.